This video is about making measurements using a Vernier calipers. Now a lot of students use Vernier calipers in a laboratory. They generally understand how to make a measurement, how to take a reading, but very few ever really bother to understand the principle behind the functioning of a Vernier calipers. So the focus here now is to see as to how it functions. What is the working principle? How do we arrive at a certain least count? And then very briefly how we take a measurement. Now everyone's seen a Vernier calipers in a laboratory. It looks somewhat like this. It has a long main scale and a slider here which can slide over it left and right. There is a scale on this main ruler here which we call the main scale. It's a straight line and typically 1 mm markings here, and on this slider as well there is a smaller scale called the Vernier scale. This too has markings, typically 10 markings, and we will discuss what's the size of those markings. So we have two scales here, the main scale and we have the Vernier scale. Now anything that's to be measured has to be fixed between these external jaws. Sometimes we want to take inner measurements, like for instance the inner diameter of a pipe, and for that we have these internal jaws. For measuring external dimensions of things we have these external jaws, and in this particular case we are measuring the length of this red colored object. Now how length measurements happen and how do we arrive at a certain least count, we are going to discuss that now. In a typical laboratory Vernier calipers, you have on the main scale 1 mm markings. These are 1 mm markings, so the length from here to here is 1 centimeter. These are 10 markings of 1 mm each. And on the Vernier scale, again we have 10 markings, but the 10 markings on the Vernier scale are equal to 9 markings on the main scale. That means the 10 markings on Vernier scale equal a length of 9 millimeter. So 10 Vernier scale divisions equal 9 main scale divisions, which basically means that one Vernier scale division is equal to 0.9 mm. Now when the jaws are touching each other and there's nothing in between them, this is going to be the scenario. The 0 of the Vernier scale will correspond with the 0 of the main scale. This tells you that the reading of the device is 0 and there's nothing being measured. Now we know that one Vernier scale division is of 0.9 mm. Now what will happen if we insert a sheet of paper, let's say, which has a thickness of 0.1 mm, and we insert it between the jaws. We bring the jaws together and there's a 0.1 mm sheet in between the jaws. Let's see what will happen. This is the 0 of the main scale and this is the 0 of the Vernier scale. But you will see over here that the 0 of the Vernier scale is slightly ahead of the 0 of the main scale. Now we know it should be 0.1 mm ahead because in between the jaws we have a sheet of thickness 0.1 mm. Now let's have a magnified view of this. So we have the 0 of the main scale here and we have the 0 of the Vernier scale here. What will happen here is that the 0 of the Vernier scale has moved to the right, and we know it has moved to the right by 0.1 mm because we've inserted a 0.1 mm sheet between the jaws. Now here, the first division of the vernier scale will appear to coincide with the first division of the main scale, which means that this length here is 1 mm and this length here is 0.9 mm, leaving us with a difference of 0.1 mm over here. So in this particular example, what we can see is that we've been able to exactly identify a 0.1 mm shift for the zero of the vernier scale. Let's take another example, and this time we have, let's say, 4 of those sheets. So the length being measured now is exactly 0.4 mm. Now what will happen is that the zero of the vernier scale will have shifted by 0.4 mm. And in this scenario, the fourth division of the vernier scale will be exactly coincident, or will be coinciding with a main scale division. Now this length from here up to here is 0.4 mm, and the length from here to here is 4 into 0.9, that's 3.6 mm, and that tells us that the zero of the vernier scale has shifted to the right by exactly 0.4 mm. So we have been able to identify, for example, a shift of 0.1 mm, in this case a shift of 0.4 mm. Now if the nth division of the vernier scale coincides with a main scale division, the length here is 0.9 into n mm and the length here is n mm, the difference here being n times 0.1 mm, which essentially tells us that the least count of the device is 0.1 mm. We are able to identify shifts in the position of the vernier scale amounting to 0.1 mm. Therefore, the least count of the device is the size of one main scale division minus the size of a vernier scale division. That's 1 mm minus 0.9 mm. Now, how do we take a reading? When we are taking a reading of a larger object, what we will see is the zero of the main scale of the vernier scale will be slightly ahead of the nth marking, n mm marking on the main scale. So the main scale reading now is n mm. Now the object that's being measured is slightly larger in length than n mm. And how much larger? Well, that's the difference between the position of the n mm marking here and the first vernier scale division. This distance can now be estimated quite easily. This length will be n into typical, in the typical device, n into 0.9 mm, and this length will be n mm. Therefore, this difference is n mm minus 0.9 mm, and that tells you the exact distance by which the zero of the vernier scale is ahead from the capital N mm marking here. So the distance between this capital N mm marking and the zero of the vernier scale is exactly 0.1 into n mm. So the reading now comes out to be n mm plus small n times the least count, which typically is 0.1 mm. So that's how you take readings. The length of the object being measured now is capital N mm plus n times the least count of this device. Thanks very much.